Hello everybody and welcome to this SimScale webinar. My name is David Short. I'm the product manager of SimScale structural analysis. I've got a very exciting topic for you today. We are going to be looking at how our users, our customers, can couple different SimScale analyses together on the platform to really simulate some real-world environmental problems. So I'm joined today by Chantal Niebuhr, who is CTO at Energyminer, one of our favorite customers. So welcome, Chantal.
Thanks, David.
Awesome. And we'll have a little bit more of an introduction down the line. So I will give you an intro to SimScale, fluid structure interaction in general with a few different use cases. And then we're going to dig into Energyminer's case study, so how they're using fluid structure interaction and what they're doing with the results and how that really drives their design process. Now, after that, we will get into a Q&A session. So if you do have any questions along the way, please do write them into the question box or the chat box in the webinar, and we'll try our best to get to all of them at the end of the session. Brilliant. So let's get into it. So SimScale, what we are about is empowering engineers to innovate faster. Now, we really see a lot of traction within these new industries, or not necessarily new industries, but there's massive transformations going on, and really simulation is a massive part of that. So today, with Energyminer's use case, it is a perfect example of a new and upcoming company within the energy transition industry, and a great example of how simulation is used both to drive design changes as well as optimize designs down the line as well. So we'll get into the real nitty-gritty details of that once Chantal shows us a quick presentation of the company and the products that they're building. Now, SimScale, we are a 100% cloud-native engineering platform, and that means a few different things. Being 100% cloud native means that you can access it from anywhere at any time, and because the simulations themselves are actually running on cloud servers, it can be accessed at any scale. So you can run large models, small models, models in parallel, at essentially any scale within the cloud space. It's one platform, but that doesn't mean just one application. Okay, we've got a wide range of different physics on the platform, flow analysis with CFD and some advanced CFD codes using lattice Boltzmann method. We've got thermal analysis, we've got structural analysis, we've got electromagnetics coming in now as well. And it's all contained in one platform with very similar workflows, right? So that means once you've learned structural analysis on SimScale, for example, it's a very easy transition to get into some flow analysis as well. So it's one platform, but with a large set of capabilities across a broad range of physics. Because we are completely in the cloud, it enables us to provide real-time collaboration. Right? We're in a unique position to allow our customers to collaborate with one another, or within a company to collaborate on projects, as well as to collaborate with the SimScale support engineers. Right? So we can you can share your projects directly with the support engineers, and we can dive directly into problems and solve them whilst you're experiencing them, rather than having a ticket-based system where it might take a week or so to have a support request answered. That is really one of the massive advantages of our cloud solution, that we can enable this real-time collaboration. AI powered is another unique position for SimScale, that because we have so much simulation data, and users can save so much of their data on the platform, it enables very high-powered AI workflows to aid in predicting simulation as well. So that's a very big topic at SimScale at the moment. We're not going to focus on that today, but if you are interested, then please do have a look online and sign up to some of our up-and-coming webinars as well around AI. I already alluded to this as well, the fact that because it's cloud native, you can run at any scale, which means both on a project scale, you can run multiple simulations in parallel, but also on a model scale, you can bring in much larger models, solve with much larger meshes, because it's not using your local hardware, if there's a problem that needs a large mesh, it's going to be run on a much larger cloud server. So if we dig in a little bit more into the physics that we have on the platform, that's quite a good segue into coupling those physics together, which is what we'll do today with fluid structure interaction. So taking an example of an electric motor, you can solve the flow analysis in the cooling chambers, for example, on a water-cooled electric motor, for example. Run the thermal analysis as well. Run the structural analysis, think about the vibration on the shaft, and also the electromagnetics as well on one single platform. Now, what we're going to talk about today is actually coupling the two on the left, flow and structural analysis, in a process called fluid structure interaction. Now, I've got a couple of examples of where that is useful and why our customers can get, and where our customers can get value out of that. So number one being aerodynamic interactions. Take a solar panel, for example. It's being hit by wind loads, and those are going to be complex wind loads, non-uniform pressures across the bodies, and having the ability to input those point-wise pressures into a structural analysis allows us to have very high fidelity structural analysis to identify high stress regions, stress concentrations, whether or not we're going above certified limits for safety factors, etc. The same applies to rotating machinery. We see a lot of use cases around running first the CFD analysis, then understanding, for example, blade deflections and expansions with the structural analysis coupled with rotating machinery. And finally, and what we're going to talk about today is actually hydrodynamic interactions. So very similar to aerodynamics, but we've got the hydrodynamic loads instead. And in this case, a hydrofoil run with first incompressible CFD analysis, and then looking at how those pressures, those hydrodynamic pressures, affect the structural response of the system as well. So you've heard too much from me already. Let's get into what's really interesting and why we're here, and that's to hear about Energyminer and some of the work that we've done together. So whilst we've been developing fluid structure interaction capabilities, we reached out to Energyminer because we knew that they're very heavy on CFD, but we also thought that there must be use cases, and they've even requested use cases around structural analysis as well, because it's critical within their design process. But yeah, let me hand over to Chantal now, and she'll give a bit of an introduction into her company and the products as well. And then I'll jump back in to explain what I've been doing with the engineering team at Energyminer. Cool, take it away.
Great, thanks, David. Yes, so I'm Chantal Nebo, the CTO at Energyminer, and we are basically a startup based in Munich, are revolutionizing hydrokinetic energy. So to explain how we are using this combination of CFD or FSI, I need to explain our product, which is the Energyfish, which is sort of the crux of our company. So this is how we are revolutionizing hydrokinetic energy. We've developed this product, or this Energyfish, that is a floating hydrokinetic turbine that stays in sort of the upper region of any canal or river section. And right now we're focusing on inland flows. And this allows us to then generate electricity locally. And what's very important to note is that this is baseload energy, which is very important for the energy mix or renewable energy mix. And another important note is that we do not install just singular devices like you see on the screen. The point of this is to build sort of a cumulative power plant, which is multiple Energyfish placed together in a river section, which then cumulatively produce quite a bit of energy and then form sort of its own power plant. So these are called schools of Energyfish and can be up to 100 Energyfish, which allow us to generate 1.5 gigawatts of electricity annually. So that's equivalent to powering 470 households, which is just from one singular river section, a significant renewable energy addition. So obviously this also means a reduction in CO2 emissions, which is sort of our goal, again, to be on this renewable energy drive and to aid this renewable energy transition. But why I'm part of this webinar today and what's important to us is the way we are producing these energy fish. So we don't just want something that is produced for now and works for a few months and produces energy, or we don't just want to sell this to someone who's going to buy it and install it and look after it themselves. We are actually running these turbines or running these power plants ourselves and doing the maintenance ourselves, and therefore we want a long lifespan. We want clean and safe production. We want clean and safe usage. We want to use recycled products, durable products that are basically in harmony with the environment. And with this goal in mind, we need to choose the right materials, choose the right manufacturing systems or manufacturing specifications to ensure this, especially because we want a 10 to 20 year lifespan. So all of our components need to be durable for that period of time. You can go to perfect. So here you can just see our first power plant, or our first pilot installation, which was here in Munich, Germany, in a canal system. And we like to refer to our Energyfish as inconspicuous power plants. And you can see here why. Although the water is very clear on these images, typically you can't see the Energyfish, you can only see part of the float sticking out of the top of the water section. And this is exactly what we want to develop, something that is not easily observed, that just fades into the landscape and doesn't have a big effect on the river section. As you can also see here, the flow is pretty much running as it should. Canal sections don't have a lot of freeboard, and you can also see the effect on the freeboard that we have there available on the side of the canal sections. So it's important to note we managed to do this without concrete, without weirs, without any heavy equipment, and that was our goal, to develop something that's easy, modular, and can be installed locally and fully reversibly. So here's just, I thought that this slide was quite good to see how we install our point that is anchored on the canal riverbed. And then we have an electricity line that runs from the Energyfish onto or to a land station on land. And we simply connect it to that connection point and then feed into the local grid. Again, this is 3 simple steps, and we've proved that we can do this in less than 60 minutes, which shows something that hasn't been possible yet, and a very quick deployable power plant, which is, again, our goal: modular, deployable, quickly deployable nature.
Awesome. Chantal, I think we might have lost you there for a couple of minutes. I'm not sure if that was on my end or if that was on your end. But I think we got the main gist of things by the end.
Oh goodness, I hope you did. I haven't lost any visuals, so I'm hoping that it continued broadcasting.
Okay, perfect. Well, it could have been me.
Should I just continue?
Let's continue.
I hope so, Dave. Okay, do you want to move to the next slide?
Fantastic.
Okay, so this is just to showcase how our Energyfish look or feed into the local grid. So we have these groups of Energyfish, which are grouped together and connected to a single land station. So we have batches of Energyfish connected to single land stations. What's important is that we feed into the local low voltage grid. So this means safe or no electricity hazard to humans or animals, which is very important and one of our goals that we wanted to achieve. Something else, just a cool part of our Energyfish is also we have self-cleaning capabilities. We want to do as much remotely using our remote monitoring IoT platform as much as possible, and to prevent having to go to site. So we have a lot of things that we are controlling remotely, like a backflush function, to ensure that we can just minimize maintenance. So the last technical slide is just to show basically, or to give an overall picture of our Energyfish. So the size of one Energyfish is about the size of a smart car. So it's about 3 meters long, 2.4 meters wide, and 1 meter high. So this allows us to get into most of the river sections throughout Europe, and just allows, again, this modular nature, not taking up, again, too much of the river section. It weighs around about 100 kilograms and swims or floats on the top section of the river. So one Energyfish, here you can see the power curve on the right, can produce up to 6 kilowatts. Obviously, this is at very positive flow environments where you have 2.5 meters per second. But typically, and what we basically designed our whole business case around is at a average power output of 1.8 kilowatts, which is easily obtainable in what is available in most river sections.
Yeah,
so again, then, yeah.
For a bit of context there, so what's a typical river speed? I have no idea, to be honest.
So typically rivers sort of not in during flood events are typically flowing at between 1.5 and 1.8 meters per second at a good site. So those are the sites that we're looking to get into. We have you have a lot of canals and slower river sections flowing at 1.2 meters per second, but we are also feasible in that region. But obviously that's not the higher flow velocity you have, the more profit you're making. So it's always better to find the better sites or the higher flow velocities. But typically 1.5 to 1.8 meters per second is where we can sit at. For instance, if you think about the Rhine River, there we have a lot of sections flowing at 1.8 meters per second, which is sort of optimal conditions. And that then gives us an expected average performance of between 180 and 200 kilowatts.
Okay.
So
this explains, so that your engineers were saying that we're going to look at 2 meters per second as a sort of top end operating range.
Yeah. So that would be sort of where we want to ensure that we are not destroying our Energyfish through continuous loading. Perfect. So the last slide, David, is just to explain how we are using, or why we are looking at SimScale, or why we are using this FSI analysis. Because obviously you can imagine a structure that is around about the size of a small car is expensive to transport and test in laboratory environments prior to starting the manufacturing process. Obviously, once we have our first Energyfish, or this type, with the new product features or the new materials that we're using, we can test this on site and we can test it in labs. But at the moment, we need some type of starting point. And we have very complex hydrodynamic loads on the structure. So just doing a simple wind loading analysis isn't always sufficient, especially because we have these complex rotating propellers that we wanted to incorporate sort of what we found in our CFD. And this allowed us to actually use those results and to get an indication of what is the durability, what manufacturing guidelines do we need to specify, and to just give us an idea of our structure response to the loading that it is basically exposed to every day. Yeah, so then I think that's it from my side, David. I hope that gave a bit of an introduction to the Energyfish.
Absolutely. Well, thanks so much. So yeah, to then explain a little bit about what I've been doing with the Energyminer team is really leading on from what Chantal described there, and actually bringing hydrodynamic loading, really complex hydrodynamic loading cases into structural analysis. And the beauty of it is that really that you do it once with your rotating CFD analysis, and then you can do a lot of optimization off the back of that one analysis in the structural world. So it's a really efficient way to do large design space exploration. And I will present that now. So we'll get into what we've been doing in the project, and the actual outcomes, the insights we got from the simulations, and I'll also show you live on the platform how it all works. So in terms of project scope, as Chantal explained earlier about the operating conditions that we're expecting to observe for the Energyfish, so it sounds like 2 meters per second is the absolute top end of the operating conditions, and that's where we need to design the Energyfish to withstand the hydrodynamic loading. Some objectives of the analyses is firstly to investigate what happens to the structural response, the stresses, the deformations when we include a cut in the Energyfish such that it can fill up with water. So typically when you make a cut somewhere, it's going to increase the flexibility, it's likely going to increase the stresses as well. So we need to ensure that when we do provide a cut to include the water, it needs to withstand this with the structural response. Okay, and why does it need to be filled up? So Chantal explained this to me earlier as well, that once you fill it up with water, that's going to allow for the correct buoyancy of the Energyfish, and also to provide that internal support through hydrostatic pressure. Secondly, we'll be understanding the survivability of each design candidate. And thirdly, we will be selecting an optimal thickness or comparing a couple of different thicknesses while to take a look at the trends, right? What happens when we do thicken the parts, when we reduce thickness, and really lead us down the line of high potential design ideas. We'll select one design candidate for further investigation from the design study that we run. So the one-way fluid structure interaction process, it goes like this. You run your flow analysis on SimScale. You have a look at your pressure results. You then download your pressure results, and it's going to be the point-wise pressure. And then we can input that as a CSV file format into the FEA boundary conditions, into the pressure boundary condition in the structural analysis. So this is the first step in coupling analyses. In the future, this will all be maintained directly in SimScale, and we'll be coupling different analyses together. We'll look into two-way fluid structure interaction as well, but this is the first step in the roadmap for fluid structure interaction problems. Okay, so once you've got your pressure results in as a boundary condition, then you run your structural analysis as normal. Now, the development that we've done is enabling this 3D boundary conditions for pressure to essentially accept a nodal mapping of the CFD pressure results. So if I bring in a live demonstration now, and we'll have a look at the work in action. So it's been quite nice. So typically I only do structural analysis at the moment, being PM or structural, but this project has given me the opportunity to get back into CFD, see some more particle traces, which I've missed over the last couple of years. But yes, this is the hydrodynamic analysis of a symmetry model of the Energyfish. So you can see we've got the rotating zone causing rotation in the fluid around the turbine. We've got some, you can see the wake details in the cutting plane, see the particle traces showing the hydrodynamic behavior of the flow. And most importantly, on the body itself, we have the pressure. This is the nodal pressure, so the pressure on each node on the surface mesh of the Energyfish. Now that's what we need for the structural analysis. So all we need to do is go to this button here, download that result, and then we'll be able to use that for applying the pressure boundary condition in the structural analysis. So if I now bring in the structural analysis itself, and we can have a look at the design study that we've been running. Okay, so as you can see with SimScale, it's a single platform. It looks exactly the same for CFD and for FEA. It's just we're going to be, rather than creating a flow analysis, we're going to be creating a structural analysis here. And I've created a few, or actually the Energyminer team, I'm not going to take credit for all of that. The Energyminer team have created a number of simulations here and shared them with me. So what we have had a look at are some different scenarios. So we've got Energyfish design number 1. We've taken out the turbine for now because that's not our area of interest. What we're really interested in is the maximum deflections and stresses within the plastic part itself. So the actual hydrodynamic casing and shrouding around the turbine. What we've done is set up a very normal linear static analysis to begin with, and applying that pressure boundary condition on the full model as XYZ pressure. So this is then uploaded as a CSV file. It's a gigantic file full of all of the CFD results on those surfaces that we've extracted from the CFD analysis. Okay. Then what we've done at a symmetry plane, just to take into account the symmetry of the model, and we've given it a fixed support to constrain the model. We've run with second order meshing. What was the mesh we used? So I wanted to get a nice fine mesh for the final results, where we've got two second order elements across the thickness of the parts. I'm using tetrahedral elements just because they're much better at capturing that curvature and slightly more complex geometry that we see here with the shape of the Energyfish itself. So this is the design number one, which is a 5mm design. So the thickness of the plastic sheet itself is 5mm. And in this design, there is no cut. So the cut location, let's see if I can find the cut. Here's the design with the cut itself. So we've put a cut between the sheets, which will allow the Energyfish to fill up with water, right? So that then we'll have the hydrostatic pressure within the model, and that's a requirement of the design. But the Energyminer team, they needed to know, hey, how much effect does that actually have on the structural results? So we can have a look at that now. We've run basically the same analysis, just with a different model, and we can do that in parallel in SimScale. So all of these simulations can be run at the same time because it's not using any one local piece of hardware, it's using multiple cloud servers. So we can go in and we can have a look at the results. Firstly, looking at the displacement. So I've got the displacement is white to black, seeing our maximum displacement of about 11mm here in the bottom. And if I just reduce the part coloring a little bit, I've also created an ISO volume showing us where we have von Mises stresses above 1 megapascal. So this is to show, you know, where are we expecting high stresses, where might be some regions to investigate further for strengthening the product. So here's the areas where we have some stresses above 1 megapascal. Now, what's great about the platform is that we can compare directly here with results from other simulations. So if we want to compare with the 5mm design, but with the cut in the back, let's have a look at that. Okay, so same thickness, but with the cut in the back, and there we can see we've got massive deformations, essentially. Massive deformations and much greater regions of stress. Now, these deformations are actually so big that a linear static analysis isn't quite going to cut it for getting accurate results. So what we actually need to do is run this as a non-linear static analysis, which I've done here, and then we can see the accurate results for the large deformation problem as well. So SimScale isn't a basic FEA tool, right? We've got non-linear capabilities, we've got dynamic capabilities, vibration, and you can do that all with the same workflows, right? So then you have the ability here to then come in and check the with cut versus without cut deformations and peak stress regions. Okay, so this is the non-linear shape, that the accurate resolution of the large deformations. Okay. Now let's have a look at the effect of increasing the thickness. Okay, so this is clearly not acceptable. We've got massive deformations. We would be expecting these sheets to contact and interfere, collide, cause noise, cause vibration. A bit of that is potentially okay, but it would require further investigation to understand if when we use those contacts in the simulation itself, how does that affect the actual deformations around the main area of concern around the turbine shrouding itself, this surface in here. So now let's go and have a look at outside of compare mode. We need to compare the 5mm with the cut, because we need a cut for the hydrodynamic design. We can take a look at these results. that we've just seen and compare them. I've got a safety factor in here as well, but let's go now and compare these against the same design but with 8mm thickness sheet metal. So if we go compare to 8mm thick, and again we're expecting some large deformation, hopefully not as large as with the 5mm, but we'll still need a non-linear analysis to get accurate results here. And there we can see dramatic improvement in both the deformation and the stress regions of the problem as well. Okay, so that is a very quick run through of the design study that we went through, and I've summarized that in the slides here. So if we go jump back to the slides quickly. So the design insights that we've got out of the project. So remember, this is early stage. This is concept design, and we want to know which designs are definitely not acceptable, which designs have high potential, and we should investigate further. So from running those 4 simulations, or actually 6 simulations, including the 2 nonlinear, we can see the following insights: that increasing the thickness from 5mm to 8mm reduces deformations by about ×4. Including a cut increases deformations by at least ×10, and for the 5mm case, that's even above 10 times the deformation that we see. And I think it's clear to say that the 5mm design with the cut produces areas of high stress and unacceptable levels of deformation. Okay, so really the design to focus on is design 4 for the time being, and this is brilliant, right? Because we've already disqualified poor design candidates, which means we're not going to spend any money on those design candidates in physical testing. We can throw them out now, and we can focus just on the high potential ideas and go into further analysis with SimScale. So we don't have enough time for that today, but I just want to highlight the next steps that can be achieved with SimScale for this project. So, and this is what the SimScale and the SimScale support team and the Energyminer team will be doing in the coming weeks, is to go down the next steps of structural analysis. So investigating the contact between the outer and inner sheets to ensure that no deformation in the turbine shrouding. So for that, we'll need a non-linear contact analysis. So just like we've done with the large deformation analysis, but include some non-linear contact as well between the sheets. We'll want to trial some alternate cut geometry. So potentially there could be different ways of making the cut, maybe not as a full cut, for example, to improve the stiffness and deformations in the product itself. So we can trial some alternate cut geometries. We can also investigate creep over the product lifetime. So when you're under these constant hydrodynamic loads, we actually have to start thinking about if creep of the material is going to play a role. So that's an important nonlinear effect that can, or time-based effect that can be brought into the nonlinear simulations on the platform. It may be interesting to look at some extreme weather conditions, so flood weather conditions as well, to really make sure that we've got survivability under all of the conditions that it will be exposed to. And then as a slightly larger project is to get into actually the transient analyses. So obviously when you're running fluid dynamics, actually in hydrodynamics, you're going to have these vortex being shared. You're going to have highly transient effects in the wake regions. And it may be interesting to understand, how does the transient pressure affect, for example, the dynamic response of the structure itself, whether that be vibration, whether that be some dynamic amplification effects, whether it could be fatigue as well. So there's a whole number of different concepts that we can get into, but today we've highlighted the more basic design level simulations that can be used as a first step to disqualify poor design candidates and really then focus attention on the high potential designs for physical testing. So I hope that was clear. That was a lot of information in a short amount of time. So yeah, I will invite all of you to let me know if you have any questions for either myself or for Chantal. we can get into it. So, what did you think, Chantal? Was that fairly clear? Did we get the point across, do you think?
Yeah, I think so. The exciting bits of it, definitely.
Awesome.
And how easy the process is.
Great. And so, in terms of next steps for Energyminer, like we've got these simulation topics that we can carry on with, but are you already getting to the point of physical prototyping?
Well, we would still like to do a few more tests. So this was sort of our first step with SimScale to test if this replicates the real conditions, because I know you're also still investigating the applicability of this or the results. And we actually had external consultants also validate our results, which was great for us. And this is exactly sort of the first step that we wanted to take. And now we would want to test different configurations, like you mentioned, look at maybe different load cases in terms of different flow velocities, and do all of those tests before we get to then manufacturing and doing destructive sample testing. Yeah, but that would be sort of the next step.
Okay, awesome. So the questions I can see, they're quite admin related. So nothing particularly technical that we need to discuss online. So unless there are some technical questions, then we can close the webinar. So I'll give it another couple of minutes. If you do have technical questions, I'll answer all of these other questions about getting signed up, certificates of attendance and things like this for I'll answer them via email. But I think it'd be. Here we go. Here's a technical question. We might have missed it, but how did you model the rotating zone for the turbine? Okay, now you're quizzing me on my CFD knowledge, but I believe we ran this with a multi-reference frame steady state approximation for the turbine. Is that right, Chantal?
Yeah. So we actually, that was a worst case scenario than looking at the transient analysis. That's why we took the steady state results. We compared both initially, but yeah, it was using a moving reference frame, so to model the blades.
Awesome. Okay, great. Well, I think that's all the technical questions, and if there are none more, then we can close up today. It's been an absolute pleasure to learn a little bit more about Energyfish and for letting me really get into the project with your engineers. That was great fun. Also fun for me to get back into CFD. So thanks a lot for that. And yeah, so Chantal, thank you so much for being here and for presenting your product, your company, and I hope it was fun for you as well.
It definitely was. Thanks, David.
Brilliant. Thank you so much, everybody. Until next time. Bye-bye.